All right, so if you're a developer, you've almost certainly felt the pain of building a search feature. You know, that constant struggle with simple keyword matching. Well, today we're going to move way beyond that. We're going to dive into the engine that's powering a ton of modern AI applications, vector databases. Let's break down how these things actually understand meaning, not just the literal words on a page.
So here's the plan. We're going to start with why the old way of searching is so limited. Then we'll get into the big idea of searching by meaning and the tech that makes it possible, embeddings. After that, we'll see how you actually measure that meaning, get our hands dirty with some practical data prep, and finally put it all together to see what a real production system looks like. All right, first up, the limits of keywords. Let's talk about why your trusty old SQL database just falls short for this kind of task.
Okay. So imagine this. An employee asks a super simple question. What are the clothing rules? Now, as a dev, what's your first move, right? You probably jump to an SQL query with a like operator. You're basically just doing a glorified string search, trying to guess the exact keyword they'd use. Maybe something like clothing.
And what do you get back? Absolutely nothing. Zero matches. And why? Because the actual policy document says dress code, not clothing. Your standard SQL database has no idea, like zero clue, that those two things mean the same thing. It's just matching characters. So this right here, this is what we call the semantic gap. It's this massive difference between how we humans talk and think and how computers just literally store strings of text. And bridging that gap is precisely what vector databases are designed to do.
So, how do we actually make that leap? Well, it's all about a huge shift in thinking, from searching for values to searching for meaning.
Yeah, this is the core idea right here. We're moving away from searching by value, that exact like keyword match, and shifting entirely to searching by meaning. We want to match the semantic context, not just the characters. Now, there's a really important trade-off here. The burden of figuring out the right search term completely shifts. It's no longer on the end user. Instead, it's on us, the developers, to do more work up front to set up the database and prepare the data properly. Okay, so let's get into the real magic behind all this, embeddings. This is how we translate messy human words into something a computer can actually work with. So what exactly is an embedding? At its core, it's just a numerical representation of a piece of text. Think of it as a big list of numbers, a vector, that an AI model spits out. But this isn't just a random list. It's a carefully crafted vector that captures the semantic meaning of that text. For example, a good embedding model just knows that the words holiday and vacation are super similar in meaning. I mean, think about it. They don't share any letters, but the model understands they're conceptually almost the same thing. And the cool part is, this isn't just a vague feeling. It's mathematically provable. The system can compare the vectors for these two words and spit out a similarity score, in this case, 87%. It can literally quantify how close they are in meaning. Okay, so this brings up a really good question that you're probably thinking right now. Why do these embeddings need so many dimensions? Why are we talking about vectors with like 384 numbers or even more? Well, it's because language is incredibly complex. Each one of those dimensions can capture a different piece of the meaning. So one dimension might track the topic. Another one could represent sentiment. Is it positive or negative? Another one might track formality. All these dimensions together create a really rich, detailed fingerprint of the text's meaning. All right, so we've got our text turned into these fancy high-dimensional vectors. The next big question is, how do we actually use them to find stuff? How does retrieval work? Well, instead of looking for an exact match, we do something much smarter. When a user types a query, we first turn that query into a vector too. Then we use a distance metric, a common one is cosine similarity, to find the vectors in our database that are the closest to the query's vector in that high-dimensional space. It's all about finding the nearest neighbors. And this is where it gets really powerful. Check this out. A user asks, "Can I take my company laptop to Florida?" The system is smart enough to know this isn't really a question about the state of Florida. It's about company equipment and remote work. And boom, it correctly pulls up the remote work policy. But now, look at this. Same keyword, Florida, but a totally different question. Can I use vacation for a Florida trip? The system immediately gets that the context has shifted. This is about time off, not equipment. And so it correctly matches the time off policy. You see? Same word, completely different context, and it gets the right answer both times. That's the power here. Okay, this all sounds great in theory, but to make it work in a real-world system, there's a super important practical step we have to talk about: data preparation, specifically chunking and overlap. So you can't just take a massive document and create one giant embedding for it. It just doesn't work well. You need a good chunking strategy. The right way to do it is to first split your text along natural breaks, like sentences. Then you group those sentences into chunks of whatever size works best. And here's the key part: you need to add some overlap between the chunks, maybe a sentence or two. That way, you don't accidentally slice a key idea right in half and lose the context. All right, let's put all the pieces together now. We've talked theory, so let's see how this all comes together to build an actual production system. And here it is. This is the payoff. Look at these questions. The very same questions that completely failed with our SQL-like query are now getting perfect, context-aware answers from the vector database. It's not just a small improvement, it is a total game changer. So, if there's one thing to take away from all this, it's that vector databases are so much more than just a fancy search index. They are a genuinely fundamental piece of technology. There was finally bridging that semantic gap, allowing our applications to start understanding information in a way that's much closer to how we humans do. And that kind of leaves us with one last big question to think about. Right now, we're getting really good at closing the gap between words and their dictionary meaning. But as these models get even smarter, what's the next semantic gap we're going to have to solve? What's the next level of understanding, maybe something like intent or even causality, that we as developers are going to have to figure out how to bridge?